Today I'm with Ezequiel Garcia. I'm Nicolas Dufresne. We both work at Collabora. We both work together on the Video4Linux, well, the Linux media codec integration. So Ezequiel is a kernel developer for actually actively working in the Linux media subsystem and contributing to getting some good progress upstream in the kernel in every sphere that are going on. Today we're going to talk to try and get you an understanding of discovering the Video4Linux codecs on your computers and your boards. Quick overview of what we're going to do. We'll speak about what we call the stateful codec. We'll describe what's the probing process to find those stateful codecs. Pardon. We'll speak about the media controller, the GStreamer codec probing, and the GStreamer codec. So I'll let Ezequiel start with what it looks like on the Linux kernel to start with.
Okay, so is this thing working? Yeah. So thank you very much, Nicolas. So hello, my name is Ezequiel. I work in Linux. Like Nicolas mentioned, despite that, I think I'm a fairly nice guy. So, yeah, I'm a human being. So I will start by describing some of the codec API we currently have in Video4Linux. So it's going to be a technical talk, but I'm not going to be digging too much. It's going to be just a presentation of the interfaces and the state of the union, so to speak, in codec Video4Linux. I hope it's not too boring for you. So before I describe the APIs itself, let's take a look at how the support looks like, because many people don't really know about this. Many people have asked me recently, so how is the mobile platform support for hardware decoders? So we do support a number of platforms. We support Freescale, we support MediaTek, Samsung Exynos,
Snapdragons,
yeah, Qualcomm.
On Qualcomm, yes.
Yes, and there's some new support incoming for Cedrus. You know, the Chinese SoCs,
the all-winners SoCs.
Yes, the all-winners, and also Rockchip.
Did you mention Amlogic?
No, I haven't.
And there's also work coming on Amlogic, and there's work coming on a well-known Raspberry Pi, actually.
And NVIDIA.
And NVIDIA also.
Right. So I think we support most of the SoCs out there. So the stateful codec API. Sorry, the stateful codecs are supported by the typical Video4Linux API. There's not a new API. It is the same API we use for video capture. Okay, I'm going to talk about that in the next slide. And then there is a stateful specification that is being written. The stateful spec specifies exactly what is to be expected from device drivers, how they should behave. Exactly, so they can be supported by applications the same way. This is not really complete as of today. It is a patch that is being discussed. It's just documentation patch that is being under discussion. I think it's in good progress. It should be done by this year. And then we have a different type of codecs, which are the stateless codecs. They're also known as hardware accelerators. And for those, we have a new API, which is the request API. So I don't know if you have heard about this. No, okay. So the request API is a completely new API that sits on top of the traditional Video4Linux API. By the way, who has worked with Video4Linux? Okay, so you know the API. Okay. You know the API? Right. So the request API sits on top of the normal Video4Linux API, and it adds a concept of these things called requests. The requests allow to do a number of interesting things, such as associate buffers synchronously, metadata. So I'm not going to be talking about that much. Yeah. So the request API also has its own spec, which is also under discussion. So the stateful codec API basically it's the same as the Video4Linux API. Like I said, you have a number of system calls, and these system calls basically allow you to negotiate the format. You can see there in the first ones are the ones where you negotiate the format. You get all the format that is supported by the hardware. You then eventually set the format. Then you can set your memory. You have to say, okay, I'm going to be doing DMA buff or mmap or whatever. And then there's just this little loop here doing the capture itself. In the case of some, for instance, decoder, this little diagram is actually duplicated because you have to do it on the input side, and then you have to do it on the output side. But it's pretty much the same. There is nothing new. So how do we discover? How do we discover what kind of decoders? What is the hardware we have? So we can later make the filters for that, which is what Nicolas is going to talk about. Well, basically the format is actually negotiated on the different pads we have on Video4Linux, which are not called pads. They are actually called the output side and the capture side, something like that. But it's the same concept. And actually, the negotiation is done with those two system calls, where you basically get all the format that the hardware can do, and from that you kind of infer if it's a decoder or if it's a capture or whatever it is. So, for instance, if the input side you get that it can deal with say JPEG, and then the output side will deal with RAW, then you know it's going to be a JPEG decoder, right? It's not much complex. Okay, now for something completely different, we have a new API right now in Video4Linux, which is not really for capturing. It's actually for topology, description, something like that, which is called the Media Controller API. This API is traditionally used to configure complex pipelines with sensors and Bayer filters and whatnot. But it can also be used to actually describe a codec, because since it allows you to tell what the topology looks like, we could also leverage this to different kinds of diagrams, of descriptions. So let's see how this would look in our case. We would have these three little blocks here. They would say, okay, I have this entity here, it is the source one, I have the decoder one, and I have the sync one. And both the source and the sync relates somehow to the /dev/video something device node.
I would like just to mention that this source and sync terminology is exactly what you find in the Linux kernel, so exactly what you're familiar with in the GStreamer framework. So that's a nice interesting fact.
Yes, I think we did that because of GStreamer probably, or...
Well, I think the author knew a bit about GStreamer when he created it.
So what is nice about this API is that it would allow us to make the description less weird, maybe, instead of these, where you get the formats in one side and then you get the format on the other side, and you have to somehow build knowledge from there. You have some kind of more, let's say, direct knowledge into what is actually the hardware doing. I think that's it for the Video4Linux side. Thank you very much for listening.
So one thing Ezequiel didn't say, he was sparing you the detail of the Linux kernel implementation, but I'm going to bring you a bit of the detail of the GStreamer implementation, which is, I believe, the part that you're most likely to well understand. So we'll go a bit over an overview of how we use these kernel interfaces in order to bring those elements into the GStreamer pipeline. It was not a single iteration to get there, but I'm just showing what the state of the art as of today. So the basic, when you got Video4Linux source, V4L2 source, V4L2 sync, you have a device property, you can configure the device property. If you don't want this to, you don't want to do it yourself, you can use the device provider from V4L in order to get the device, and that can be used to configure the element for you. This is nice, this is discoverable, it works, but it's not very convenient for the codecs where you actually need to, you actually are going to use encode bin, decode bin dynamic elements. It's too slow actually to go navigate through these things. So usually you would prefer to just do the probing once, cache it into the GStreamer registry, and let's see how it works. So, same thing as Ezequiel described earlier, but what we do is that we want to do it once. So we move that code into what the plugin entry point. So GStreamer has a plugin, it has an entry point, it's a good place to do stuff. So in this function, we're going to iterate all the video nodes that we find. We get these videos usually through to UDEV, but it's an optional dependencies. So we have other methods to enumerate the devices. So we'll open the device, we'll do the famous query caps, we'll enumerate the format, and we'll come out with a classification. Classification because you don't know yet what it is. It could be an encoder, a decoder, or something else. So the classification, what we're looking for on the capability fields, actually, it's a flag that is called V4L2 cap video M2M. So it means that it's a special driver that has two queues. So there's an input queue and an output queue. It's really funny because the input queue is called output and the output queue is called capture. So we'll try to avoid these terms actually in the presentation, and I'll use the term source and sync, which is used on the underneath media controller, and that makes much sense for us. So after enumerating the formats, what do you get? So how do you identify basically the decoder? So you would enumerate formats on the sync, and basically you're expecting to have all encoded formats, and then you would enumerate the formats on the source. And you're also expecting to have only raw data actually coming out of a decoder. That's the representation we have actually of a decoder. And for the encoders, it's obviously the opposite. So this classification is it's being inferred. It's not explicitly exposed by the Linux kernel, not at the moment, but seems to work so far. It's been running for a couple of years, especially for encoder decoder. There's pretty much no misidentification so far. What is really interesting about the classification is that we actually use the GST caps mechanism to do this classification because it's no code. So what do? We enumerate the format on one side, on one queue, and we make caps out of it. So here we got raw caps. And then we list every raw caps we know from the V4L framework, and we actually make a caps out of that. On the other queue, same thing, but we'll enumerate again the formats. It will give us probed coded caps, and we also make a list in the caps of all the known coded caps. Now, if you do the intersection, if you use the GST caps is subset, what it will tell you is that your probe caps are, if it's true, it's because your probe caps are limited to actually being raw caps or coded caps. In this case, we have raw and coded at the output, so we have an encoder. And if you meet those two conditions, you have a classification. So you can now, you know what you have in hand. Now it's not enough. So what do we got? Now we got caps. Those caps, what are they? So the caps actually represent a subset of what your hardware is going to support. So it's a good fit for your template caps. So if you were to write manually your element, you would use that as your template caps. And we also have a path actually to the driver, and that is what would be in the device property. Now, how do we wrap this into GStreamer so when you create an element in the registry, it does the right thing? Yes, okay. So the trick we use, it's quite it's the only time in my life I've ever used that mechanism in glib. It's probably the last time also. We do dynamic subclassing. So dynamically at runtime, we will subclass a class that we implemented manually in C, and we will pass parameter to the class initializer sorry, in order to tell the subclass that there are specific properties. So basically, we already have that class, but it's abstract. And we're going to subclass it and tell it this is the device and this is actually the template caps that you need to expose with this name. And that it's not possible with the usual conventional macros because they cast the functions that you have to initialize the class and hide actually all the information you would need to get the actual class data. So we do it manually using the G-type info structure with the class in it that allow for the class data to be passed. And we wrapped all the information we want in the class data. And then for each element, we register them with a unique name. Actually, one driver can support multiple codecs. But for simplicity and usability, we expose each of the codec as its own element name. So you'll have a nice V4L2H264 DEC, V4L2H264 ANC, and you have this for a wide amount of codecs. So whenever you program your pipeline, you just need to remember these names. Previously, if you remember, it was called V4L Video0 DEC, and that would support all the formats supported by Video0. The problem with that is that, you know, those video nodes, their numbering are not fixed. They move from boot to boot. So you never know where it is. You can't really use them statically. And because I have time, that actually raised a bit of problem, a conflict with the registry. So as soon as you put that in the registry, those classes actually become kind of outdated. So you need a mechanism to keep them up to date. And one of the big features of the registry is that you can actually pass a list of directory, files, environment that would actually trigger a cache invalidation. And because those devices are at different places at every boot, and they might not be on the next boot because they removed the driver, or they might be on the next boot because they added the driver, we basically need to probe every boot. So we added the device node, which is different between every boot. And it won't change actually further unless you unload and you reload your device. And the device becomes different for the only reason that you have UDEV running on your system, and it removes the node and it adds a new one. If you don't have UDEV running, that mechanism doesn't work for you. But because we're using fixed name these days, it's less of a problem because whenever you create a plugin, it will reprobe and find the actual device that it needs to be used. The only problem is if your hardware changed, and in which case you might have the wrong codec actually exposed. So that's the technical part done. Now we mentioned about stateful, stateless codec, and I don't think we really explained what this was about. So,
yeah, actually,
oops.
Actually, I forgot that I had brought a board here with the stateless codec,
yeah,
just to show you.
So, who in here I've ever used a VAPI actually accelerator on Intel? So, who knows that VAPI, the driver, is not really a complete H.264 decoder? So, exactly those people knows, but not everyone. Basically what VAPI exposes is an accelerator to do the actual mathematical operation in the process of decoding in H.264, H.265, or other codecs. And what the kernel stateful vs stateless codec are is that the stateful codec in the kernel is a complete kernel. It's a complete decoder. You give it a bit stream, it gives you a frame. With the stateless codec, like on Allwinner, you just have an accelerator, which is pretty much what Intel do with their VAPI driver. And you still need to do all sort of DPB management, ref list management, error concealment, and error detection, error handling. Everything has to be done in user space. So there's it's probably not half because there's a lot of math in the process of decoding, but I would say it's probably about a third of the decoder that has to be implemented. So where we're going with that, so there's stateless codec that are coming on little chips, on little hardware, and we'll have to support them, and we don't really have time to support them. And at Bootlin, actually, they came up with a VAPI driver based on the V4L2 request API. So this one is using those famous requests. And that allows us actually to reuse GStreamer V-API, which already implements good bits of these decoders in order to operate those elements. It does not work yet. GStreamer V-API needs love, but we think it's a good way actually to bring forward more developers toward trying to fix GStreamer V-API instead of trying to just complaining about it. So hopefully that's gonna get more people to the community. Those accelerators are much simpler, much more robust. There's no chance of hanging your GPU because it's not a GPU. It's a discrete hardware. So it's totally independent. There's no complex state machine that need to cooperate with your GL driver. So we also have hope that it will be more stable. The only side effect is that everybody knows that so far it has been quite unstable with the VAPI. But we can't really blame VAPI because it doesn't do much, really. It's a big, huge table of everything that is defined in the specification. And the operation are execution-centric. And most of the problem are actually GStreamer code because that's our only codec that we ever implemented in GStreamer. And we just need to put more time on it. And we think that's the best way to get running.
Yes, when Nicolas says we, it's actually the V4Linux guys. We have this meeting during I think it was Tuesday,
yeah.
And we considered all the options, and so we have decided officially for short term, the quickest way to get there, to get GStreamer VLC and etc. working on these mobile things. It's going to be via VA API.
And I believe as we get familiar with this, and we are aware of little difference between VA API and the kernel interface, but they're relatively small. And we'll be able to better give what's the direction forward, what's the future about this. And there's things that I want to address, especially in GStreamer V API, that if we ever decide to have a V4L version, we're probably going to share the code and fix bug in V-API at the same time. Notably, double parsing is one of the big issues, the big overhead actually of that system. So we parse in H.264 parse, and then we parse again in GStreamer V-API. And we already have plans to fix it. We just need to put some hands on it. And yeah, and meanwhile, Ezequiel's gonna make sure all the driver works. Every one of them. We already have one for Cedrus, and it's in pretty good shape. It's quite powerful for the dollars. So if you ever look at the price range of this device, it's impressive. And same thing on the Rock chip. Which one?
The Rock chip. Well, we have codecs on the 64-bit versions, which is Arcade 3399. Which powers the Kevin, the Samsung Plus, Google.
Right. Oh, but
Chromebook.
Yeah, that runs on the Chromebook. That's true.
Yeah. And a bunch of other Chromebooks also run on Rock chips.
The big secret thing about stateless codecs, so they're cheaper, but also they're naturally multiplexable. You can have as many instances as you want because it's the upper layer that keeps the state and push the state into the driver. You don't need to use, you can use multiple stream and push different state into it.
And you can see that if you try to play some videos on some of your, well, you have to pick a Rock chip Google Chromebook device, but I was wondering exactly that, and I was thinking, okay, the first one is playing. Now the second one is going to crash, right? Like, No, it played. Now, okay.
It played, but it's slower.
Fourth, okay. Yeah. The fifth one is going to play slower.
So it's a surprise.
They all play just well.
Yeah, but it's a surprise with the stateful codec because they might have one instance, they might have 2 instances, 4, or maybe they have 100 instances, but you never know. And sometimes when it doesn't work, it fails, and sometimes it just falls back to software. But the fallback to software might not happen on the screen you expected it should happen. And you don't have this problem because you just need to idle the other task in the case of stateless. I think that's it for today. We have time for questions. We have a good 5 minutes. So please raise your hand and use the microphone. Clearly no one's worked with codecs. Well, thank you very much. And I hope you'll be able to use codecs on generic Linux for a long time.
Thank you.